OK, so let's switch topics here. We finished our vector processors. And we're going to start talking about a technique that's looking at how to exploit different forms of parallelism, or thread-level parallelism, than we've been looking at up to this point. So this is not data-level parallelism, but this is actual thread-level parallelism or process-level parallelism in your machine. So what's the motivation for changing our computer architectures to run threads very effectively? So we've talked about threading or multi-programming in the past, where you time slice between different processes. That's not what this is about. This is about executing multiple programs at the same time, or time multiplexing between processes on the time slice of an instruction at a time. So where this really came from is that sometimes you can't really extract parallelism in instruction-level parallelism. So this is what our out-of-order processors try to exploit, and superscalars try to exploit. And sometimes you can't necessarily exploit data-level parallelism in a program, because data-level parallelism will say doesn't necessarily work out, or you don't have dense matrix sorts of codes, which is very easy to find data-level parallelism. Instead, sometimes your workloads have thread-level parallelism. What we mean by thread-level parallelism is that either there's independent sequential jobs that need to happen. And an example of this would be you have to operate on a million things, but the control flow for each of those million things is wildly different. So the most efficient way to go about doing this is just to actually have a process or a job per work unit that you need to work on. So a good example of this is network processing. You are trying to build a firewall, and a packet comes in on your network card. And your firewall wants to inspect this packet and look for, I don't know, malicious attacks. It wants to look for something like viruses, or wants to look for attack code sequences, or Trojans, or something else like that. This isn't data-level parallelism, because you can't try to have each of the operations working on these packets be the same thing. So depending on the type of packet, you're going to make wildly different control flow decisions. So for instance, if the packet is TCP versus UDP, is like a big choice at the beginning. And then what port is it on? Is it SSH? Is it HTTP? Is it web traffic? You're going to do lots of different processing in your firewall based on that decision tree. So typically, the most efficient way to go out and try to attack this is that you actually just have a job or a process or possibly a thread per data element that comes in. Another reason you might want to do this is there are examples of applications where you actually having parallel threads will solve the problem faster. So believe it or not, the traditional traveling salesman problem, if you throw threads at that, you can actually have this problem get superlinear speedups, because you can have basically other threads sort of parsing off the search tree faster. And then the threads can share data between each other. And when another thread comes to a certain point, it doesn't have to recompute a certain location. It can just use the previous result of another thread that already got to that point and know that it doesn't have to go down a certain path. So this is kind of like dynamic programming, if you will, but for some sort of large search. That's one example, as a very poignant example of having threads get you superlinear speed up. But you can also just use threads to go after certain types of parallelism that are hard to get at data-level parallelism also. You could actually hide latencies by using threads. So an example of hiding latency using threads is, let's say you have a program that you know typically misses in your cache. But you have parallelism in this program. One way to attack it is to cut up the problem and have a thread per different problem, And when one of the programs blocks on the cache, switch to the other program. So while you're waiting for memory to respond back, you can do some useful work. OK, so let's look at this from a pipeline perspective and look at ways to recover cycles. So here we have some loads. Load, something that's dependent on, we have a load that's dependent on another load, and an add that's dependent on the second load. And then finally a store, which is dependent on the add. So the downside of doing this is you get all this sort of dead time. All this purple time here is dead time on the processor. We could throw an out-of-order superscalar at this. It's not going to do any better. Yeah? So you're right. This could, if we're doing bypassing, we could pull these one cycle earlier, but we still have a lot of dead time. And if you were to have an out-of-order superscalar, out-of-order would not actually help you out in this case either, because there's an actual dependency string through all these instructions. Well, that's not great. So can we come up with some ideas to cope with this? So one thing we said is we can add bypassing to decrease the time here, but having an out-of-order superscalar is not going to make this go faster. So that technique doesn't work. What other techniques we talked about? Vector processors. Well, there's no vectors of data here. We can go wide. Well, that doesn't help. We're still going to be executing one instruction per cycle. So we can try to do a VLIW. Doesn't help. If the out-of-order superscalar can't do it, the VLIW probably can't do it. So we have all these dead cycles. We want to try to recover some of these dead cycles.